All right, let's begin Unit 4 by talking about congruent figures, which is, more simply put, how do we tell if two shapes are the same? And there's really two schools of thought. You can think of it in terms of transformations, where two figures are congruent if one or more motions or rigid motions map one figure exactly onto the other. So, for example, I know that these two green triangles here are the same because I can perform a reflection to get from one to the other. And there's also a translation, a slide, and a rotation, which is a turn. So if you can, and it's called rigid motion because it doesn't change its shape at all. It's like it's rigid, right? It doesn't move, it doesn't budge. Um, but if you can perform any of these actions to get from one shape to the other, the shapes are the same. We won't be doing transformations for this unit. We're going to be using measurement. So two figures are congruent if their corresponding parts have the same measure, which basically means we're going to be matching up sides and angles. And we can measure these angles with a protractor or a ruler. So let's practice matching up corresponding angles and corresponding sides. So the angles, these red ones here, those form a match. Okay, so we would write this as a statement. Now, they're both red, so that's probably an indication that they're the same size, but this is called a congruence statement. And be sure you write that above here, congruence statement. And we use that congruence statement to give us a sense of order to things. And another reason why A is equal to E, it's not just the color, but because A and E are both the first letter that shows up in the statement. Okay, so the first goes with the first, the second with the second, and so on. So you can fill in these angles pretty quickly without even looking at the picture. Okay, so all the colors correspond and they're equal. And you could do the same thing with the sides. For example, AB. AB is the first letter and the second letter, so EF should go with it. And if you did B and C, those are the middle two letters, so F and G should go with it. CD are the last two. And finally, if you do the last and the first, it should be the same as the last and the first. And you can see those matching visually as well. But we're really just using the congruence statement. So here, again, if we know AB, I know that AB is the first two letters, so it goes with PQ, which is here. So I know that 19 is 2y plus 3. And after a little bit of work, you'll find that y is 8. And you could do that for AC. AC is the first and the third. So I know that the first and the third go with AC. So AC is PR, and you can see that here. So it looks like AC is equal to X. Same deal here. AB should be equal to DC. So this is 3x plus 11, and this is 20. So x is 3. Again, why do those match up? Because they're the first two letters. Okay. Angles can be a little bit more challenging. For example, BCA. We would hope that it's just this angle here, because that's the one that's labeled, but we can't be sure. So BCA is the second letter, the third letter, and the first letter. So whatever angle it's equal to, it has to be in the same order. So over here, the second is C, like I'm looking right here. the third is B, and the first is D. And it turns out that that indeed is this angle here. So we do have 5y is equal to 73. And if we divide that, we get 14.6. So this says, suppose the triangles are congruent if this is 83 and WSY or YSW is 64. What is B? Well, we already know that W and B are equal. And we could find out what this angle is. Call it X. I know that if we add those three angles together, it's going to be 180. So let's call it a measure of angle B also X. Then we would have, without much work, that X is 33. And it's going to be 33 for both angles because they are both first in the congruence statement. Okay? So yeah, that's kind of what makes triangles congruent, is if all of its parts match, meaning its sides and its angles. You need 3 and 3. Okay? And here's an interesting idea. Ozzy says that N and Q match up and O and R match up. So that means that P and S must match up. Is that right or wrong? Long story short, yes, this is a true thing. Just to prove it, I don't want to go through the entire proof with you, but let's say that we knew the measurements like that. We know what this angle is from what we studied last unit. This has to be 10 degrees because it has to equal 180, all three angles together. So this one, but this is the same game, right? This is also 10 degrees. So because of the restriction of all the angles equaling 180, it makes it so that P and S are the same every time. And this is all summarized in what's called the third angle theorem. So if the reds match and the blues match, so do the purple ones. So this is called the third angles theorem because it's just guaranteeing, hey, the third ones match up too. We have a few proofs, but first let's look at this. So are these triangles congruent? If so, write a statement. So to pause and take a moment and see if you can match up any sides or angles that you know. It turns out that these two angles are the same by vertical angles, and by the third angle theorem, I know that those two match up too because I know right angles are congruent to each other. But we have no idea about any of these sides, right? So angle, angle, angle is what we have. That's not a congruence theorem. Let me show you why. This picture could have been drawn like this, right? And we still have vertical angles, and we still have the third angle theorem. But those triangles are clearly not the same, okay? Those are actually called similar triangles when AAA is applied. Whereas over here, we have a lot of info. One thing we know is the third angle theorem. We know that this angle over here matches because the other two match. And we also know that this middle edge is shared, so it matches as well. And if you count, you'll see that we have 3 angles and 3 sides. So these are congruent. And when we state the congruent statement, we want to do M, L, N. I'm going in order of rings here. So we got 1, 2, then 3. And then we got 1, 2, 3, like that. I try and go by order of the angles. Because if you remember the congruent statement, the order matters. Because we want to make sure that L goes with L and M goes with O. So, to summarize that, triangles are congruent if the 3 angles match and the 3 sides match. Okay? So, we want to show that this is the two triangles that are congruent. And before we can do anything, we need to update our picture. So these are parallel. They're also the same in length. These are the same in length. And these angles are also the same. Okay. So there's a few routes we could go. One thing I know is just like on the last picture, AC is congruent to AC. And you might wonder why I say that, but if you notice in this proof, we are listing 3 sides. This is now our third side. And this is our first angle. So this is my third side matching. And it's important that we explicitly state that matching so we can use the triangle congruence theorem. And the reason is actually pulling back from a long time ago, the reflexive property. Which says that something is equal to itself. And that's important here because that shared side is equal to itself. So that is a side that matches on both triangles. We need some work with the angles. And whenever you spot, well, first of all, we have parallel lines here, right? And if you spot this Z shape, which we will see a lot. Oh, let me try and draw it a little bit better. There we go. There are alternate interior angles right here. Right? If we like extend this, right? Those would be alternate interior, definitely interior, right? So yeah, those angles actually end up matching. Okay, so how would you do those? Maybe let's call it CAB. And how about, and I don't care too much about the order here. We're just trying our best. How about ACD? Can't say angle C because it's got 2 angles there. So this is alternate interior angle theorem from a bit back. And then once you have 2 angles, right, we do have 2 angle statements, we know we're given the third one by the third angle theorem. So let's see, that would be angle BCA. And how about DAC? Basically these ones here. Those are guaranteed by the third angle theorem that they match. And then this here is going to be the definition of congruent triangles. Okay, we got one more left. So we got given, and we got what we're trying to show, which is that triangles are congruent. So we know we're going to be using the definition of congruent triangles, which means we're looking for 3 of each, right? So these match here. These match. And then we have 2 bisects happening, okay? We have AD bisecting BE and BE bisecting AD. So we're definitely going to use bisect like we normally do on the first if it's mentioned. It's a little bit tricky here, but basically this segment here is being cut in half and we have 2 congruent parts. So this is cut like this, and then also BE is being cut into 2 equal parts like that. So we want to say AC is congruent to DC and BC is congruent to EC. So actually we have all the sides accounted for, and we have one of the angles. So whenever angles meet at a point like that, there's going to be vertical angles. So that would be angle ACB and DCE. Vertical angles are always congruent. And we need the third angle, but that's guaranteed. And this concludes the video. Okay, hopefully that helped clear up a little bit